The night sky above your head is wrong. Not broken, not incorrect in any way that would bother a physicist right now, but wrong in the way that a photograph of a river is wrong. Technically accurate at the moment it was taken, and completely misleading about what the river actually is. The river moves, and so does everything above you. The stars you see tonight are in the wrong positions. The constellations that sailors memorized, that ancient astronomers named, that every culture on Earth has been drawing lines between for 50,000 years. Those shapes are already dissolving. Slowly. Too slowly for any human lifetime to notice. But dissolving. In 100,000 years, Orion will be unrecognizable. The Big Dipper will have sheared apart into 7 unrelated stars, drifting in separate directions across the sky. The patterns are temporary. We just don't live long enough to see them change. But that's not what I want to talk about tonight. Tonight is about the change you actually would be able to see if you were standing on this planet 4 billion years from now. The change that has been mathematically guaranteed since before Earth existed. The change that is, right now, already in motion, locked in by gravity, irreversible, and producing a night sky so different from the one above your head tonight that a person from our time, if somehow transported there, would not recognize the sky at all. In approximately 4.5 billion years, the Andromeda Galaxy will collide with the Milky Way. You've probably heard that sentence before. You might have heard the word collision and pictured something catastrophic. Stars smashing into each other, explosions, destruction on a scale that ends everything. That's not what happens. And the real version of what happens is, in almost every way, stranger and more beautiful and harder to fully absorb than the dramatic version. This is the story of that collision, not the abstract version, the specific one. Real numbers, real timescales, a clock we're going to build together and then watch move, from 1 billion years from now to 2 billion to the first pass, to the chaos, through the second pass, to the merger, all the way to what the night sky looks like from Earth when the 2 galaxies have become one thing. We are going to watch the sky change from beginning to end. And by the time we're done, you're going to understand something that most explanations of this event don't get to. That the Andromeda collision isn't a disaster that happens to us. It's the next chapter of the only home we've ever had. Before this goes any further, if you found this and you're already horizontal, already drifting, that's exactly where this was meant to land. If the channel is new to you, subscribe. We do this a lot. Long, specific. We actually looked up the numbers space theory, designed to quiet a brain that won't turn off. That's the whole thing. One more ask. If you've been listening for a while and you've never commented, tonight's the night. Tell us where on this planet you're falling asleep right now. And I mean specifically where, because there is something genuinely strange about the fact that people in completely different parts of Earth, under completely different sections of the same sky, are all listening to a story about that sky disappearing. The geography of this audience matters. Drop it below. Now, back to the galaxy that is already moving toward us. That is the distance between the center of the Milky Way and the center of the Andromeda Galaxy, as of right now. As of the moment those photons left Andromeda, and are only now reaching your eye if you look up on a clear, dark night. The smudge you might find in the constellation Andromeda is 2.537 million years old. The galaxy you're seeing existed before our species did, before Homo sapiens, before Neanderthals, before the genus Homo at all. You are looking at a fossil of light, and it is getting closer. Andromeda is approaching the Milky Way at approximately 110 kilometers per second in terms of the direct line-of-sight component of its velocity. 110 kilometers per second is 396,000 kilometers per hour. It is fast enough to cross the continental United States in roughly 45 seconds. Fast enough that in the time it takes you to read this sentence, Andromeda has moved more than 500 kilometers closer. But here is the thing about 110 kilometers per second, when your starting distance is 2.537 million light-years. It is nothing. It is barely a nudge. At 110 kilometers per second, with no change in velocity, the journey would still take roughly 7 billion years. The reason the collision happens sooner than that, the reason it happens in approximately 4.5 billion years rather than 7 billion, is gravity. As the two galaxies get closer, the gravitational attraction between them increases. They are accelerating toward each other. The gap will close faster and faster as they approach, the same way a falling object accelerates as it drops. Andromeda and the Milky Way are, in the most literal physical sense, falling toward each other. This is not a collision in the way a car crash is a collision. This is two objects in a gravitational dance. One that started billions of years ago. One that is still playing out across timescales that make human civilization look like a single frame of a very long film. Let's build the clock. 1 billion years from tonight, the night sky is almost the same. This surprises people. 1 billion years is a number so large, it feels like it should transform everything beyond recognition. And in some ways it will. The continents will have rearranged completely, the sun will be measurably brighter, the oceans more threatened, life on Earth, if it persists, will be nothing recognizable to us. 1 billion years of biological evolution produced the difference between a bacterium and a blue whale. A second billion years of biological evolution from wherever life on Earth stands today will produce something we can't begin to picture. But the sky? The sky changes slowly. Slower than biology. The individual stars visible tonight will mostly still be visible in 1 billion years. Many of them will still be in roughly similar positions. The main constellations will be unrecognizable, because proper stellar motion, the actual movement of individual stars through space, accumulates over millions of years into angular changes visible to the naked eye. But the overall character of the sky, the density of stars, the broad structure of the Milky Way band, the visibility of other galaxies, will not have changed dramatically. Andromeda will be different, though. At 110 kilometers per second, plus gravitational acceleration, Andromeda in 1 billion years will have covered roughly 10 to 15% of the original distance. It will be somewhere between 2.1 and 2.3 million light-years away, depending on how gravitational acceleration compounds across that time frame. That's closer, but not radically so. What changes is how it looks. From Earth's perspective, assuming Earth still exists, which is a genuine uncertainty we'll address, Andromeda will have grown in apparent size as it approaches. Not dramatically, not yet, but measurably. If you could compare a photograph of tonight's Andromeda with the photograph from 1 billion years from now, the later image would show a slightly larger smudge of light, slightly brighter, its spiral structure slightly more resolved. Still a smudge to the naked eye. Still a patch that requires dark skies. But bigger. This is the billion-year sky, essentially familiar, subtly changed. Andromeda's smear of light grown just enough to notice if you knew to look for it. The quietness of this phase is important to understand because it sets up the contrast for what comes later. The universe is patient. It accelerates slowly. It gives no warning that anything is coming. For most of its first billion years of approach, the collision looks like nothing, a slightly brighter patch in a sky that otherwise seems eternal. There's something about the 1 billion year mark that doesn't get discussed enough in most explanations of this event. So, let me spend some time here. In 1 billion years, the Sun will be approximately 10% more luminous than it is today. This doesn't sound like much. It is catastrophic. The difference between Earth's current energy balance and a 10% increase in solar output is roughly the difference between liquid oceans and the beginning of a runaway greenhouse effect. As the Sun brightens over the coming billions of years, Earth's surface temperature will increase. Water will begin evaporating from the oceans at higher rates. More water vapor in the atmosphere creates additional greenhouse warming. Higher temperatures evaporate more water. The feedback accelerates. The technical term for the end state of this process is a moist greenhouse. Before we get to the Andromeda collision in any meaningful way, before Andromeda even begins to look noticeably different in the sky, the fundamental habitability of Earth's surface is already threatened by the natural aging of our own star. Most discussions of the Andromeda collision treat Earth as a passive observer that simply watches the sky change across the full 4.5 billion year timeline. But that framing obscures something important. The collision doesn't threaten Earth. The Sun does. We would be dealing with an increasingly hostile home star for hundreds of millions to billions of years before the first galaxies made contact. By the time the night sky begins its most dramatic transformation from the collision, the question of whether anything alive on Earth's surface can witness it is already genuinely uncertain. This is not a reason for despair. It is a reason for accuracy. The story of the Andromeda collision, told honestly, is inseparable from the story of Earth's long-term fate under an aging sun. 1 billion years from tonight, those two stories are running simultaneously, and neither one has reached its climax. 2 billion years from tonight. Now we're getting somewhere. By 2 billion years, Andromeda has closed roughly a third to half of the original distance, accounting for gravitational acceleration. It sits somewhere around 1.3 to 1.7 million light-years away. The numbers vary depending on whose simulation you're running, but the shape of what happens to the sky is agreed upon. Andromeda is no longer a smudge. To the naked eye, under dark skies, Andromeda at this distance and size would appear as a distinct structure, a faint but clearly oval form of light, clearly larger than a simple star, clearly possessing extent and shape. The brightest parts of its core would be visible as a brighter concentration at the center of the glow. The outer disk would fade gradually into the surrounding sky. On the very best nights, hints of spiral structure might be detectable at the limits of human vision, though a photograph would show them clearly. In terms of apparent angular size, at 2.537 million light-years, Andromeda spans roughly 3 degrees in its full extent, about 6 times the width of the full moon. At 1.5 million light-years, its apparent size grows proportionally. It might span 4 or 5 degrees, making it one of the largest visible objects in the sky, other than the moon itself. But the light, the total light arriving from Andromeda, also increases as it approaches. because the same number of photons are now spreading across a smaller distance. Andromeda becomes not just larger but brighter, significantly brighter. The faint smudge that requires careful observing conditions tonight becomes, in 2 billion years, a feature of the naked eye sky that no one could fail to notice. This is when it starts to be beautiful and frightening, both things simultaneously. The galaxy in the sky is not just a visual curiosity at this point. It is a gravitational presence. The massive dark matter halo that surrounds Andromeda, an enormous invisible sphere of matter, extending far beyond its visible disk. That halo is already interacting with the Milky Way's own dark matter halo. The two extended structures, invisible to any telescope, are beginning to interpenetrate. Not dramatically, not violently, but the gravitational influence of Andromeda's mass is already beginning to make itself felt in the orbits of the Milky Way's outermost stars. The outer halo of the Milky Way, the most distant stars and globular clusters orbiting our galaxy at distances of hundreds of thousands of light years from the center. These objects are already being gently perturbed. Their orbits, which have been stable for billions of years, are beginning to feel the gravitational influence of something approaching from outside. The perturbations are tiny, measured in fractions of a percentage of their orbital velocities. But they are real. Gravity does not announce itself. It simply changes what falls where. Let me break the chronology for a moment, because there's a thing about the dark matter halo that most people don't know, and that changes how you think about this entire event. Both galaxies, the Milky Way and Andromeda, are surrounded by enormous halos of dark matter that extend far beyond their visible stars and gas. The visible disk of the Milky Way spans roughly 100,000 light-years in diameter. The dark matter halo extends to somewhere between 500,000 and 2 million light-years, depending on how you define its edge. Andromeda's halo is similar, and some measurements suggest it extends to roughly 1.3 million light-years from Andromeda's center. If that's true, if Andromeda's dark matter halo genuinely extends 1.3 million light-years outward, then the two galaxies' halos have already begun to overlap, not slightly, substantially. The outer edges of the Milky Way's dark matter halo and the outer edges of Andromeda's dark matter halo, at their current separation of 2.537 million light-years, are within roughly 100,000 light-years of each other, perhaps already interpenetrating at the very outermost, most tenuous edges. The collision has, in a very real sense, already started. Not in terms of visible stars, not in terms of anything you'd see in a telescope, but in terms of the dominant mass of both systems, the dark matter that makes up 85% of their total mass. The interaction may already be underway, quietly, invisibly, accumulating gravitational influence that will compound across the coming billions of years into the more dramatic events visible in the night sky. This is what I mean when I say the universe doesn't announce itself. The largest component of this collision is dark, literally invisible. The part we can see, the stars, the gas, the glowing disk, is a small minority of the total mass involved. The collision of two galaxies is primarily the collision of two enormous structures we cannot see, driving the visible material into a dance whose choreography was decided in the dark. The question of what orbit Earth's sun will be following during all of this is one that simulations have attempted to address, and the answer is both reassuring and unsettling in equal measure. Simulations of the Milky Way-Andromeda merger consistently show that individual stars in both galaxies are not stationary within their galaxies during the encounter. The tidal forces, the disruption of the galactic potential, and the starburst dynamics all alter the orbits of stars within the merged system. A star that currently orbits at a given distance from the Milky Way's center may, after the merger, find itself at a very different orbital distance, either ejected to the outer halo, thrown into a more central orbit, or captured into a stable orbit somewhere in the merged system. The probability that our Sun ends up in a very different part of the merged galaxy after the encounter is calculated at roughly 12%. That's the chance, according to current models, that the Sun's orbit changes dramatically. Not that the Sun is flung out of the merged system entirely, that probability is lower, around 3%, but that it finds a new, significantly different orbit within the merged galaxy. An 88% probability of remaining in a relatively similar type of orbit is on the face of it reassuring. The most likely outcome is that the Sun continues doing roughly what it has been doing, orbiting at intermediate distance from the merged galactic center. Not dramatically closer, not dramatically farther. But similar orbit does not mean same neighborhood. The merged galaxy will have a different structure than the Milky Way. The familiar galactic center, the familiar orientation of the disk, the familiar directions of Cygnus and Sagittarius that define the Milky Way as seen from Earth. All of this will be different. If the Sun retains a similar orbital radius, it orbits in a galaxy that no longer looks like the Milky Way. The constellations will be unrecognizable, not just because stellar proper motion has erased them over billions of years, but because the Sun is orbiting in a merged, distorted system whose structure on the sky bears no relationship to the sky we know tonight. The Sun will be, for all practical purposes, in a new galaxy. Same star. New home. The second pass and the merger, approximately 5 to 6 billion years from tonight. The two galactic cores, having swung apart after the first pass, fall back toward each other. The second pass happens faster than the first. Gravity is now fully dominant. The two systems, their outer halos already deeply interpenetrated, their disks already disrupted, their stars already scattered across wide arcs of the merged region, pulled together with the accumulated momentum of a fall that has been building for 5 billion years. The second pass is more violent in the galactic sense than the first. The two dense central cores, each containing its own supermassive black hole, approach each other. The Milky Way's central black hole, Sagittarius A, has a mass of approximately 4 million solar masses. Andromeda's central black hole is larger, estimated at roughly 100 million solar masses, about 25 times more massive. These two black holes, surrounded by their dense clusters of orbiting stars, approach each other. What happens next is one of the most energetically extraordinary events possible in galactic physics. As the two galactic nuclei merge, a process that takes hundreds of millions of years even after the second pass, the two central black holes spiral toward each other. They shed orbital energy through gravitational waves, the ripples in space-time that instruments like LIGO and LISA are designed to detect. The gravitational wave signal from two supermassive black holes of these masses spiraling together would be detectable across the observable universe. It would be one of the loudest gravitational wave events in the history of this corner of the cosmos. Eventually, and eventually here means perhaps hundreds of millions of years after the second pass, the two black holes merge. The merger releases an additional burst of gravitational waves, and a burst of electromagnetic radiation as the surrounding gas is shocked and heated. The merged system becomes a single, more massive black hole sitting at the center of what is now a single merged galaxy. From Earth, from whatever remains of Earth, orbiting whatever remains of the Sun. In whatever orbit the Sun has found in the merged system, the merger of the galactic nuclei would be visible as a brightening in the direction of the galactic center. The feeding of gas onto the newly merged black hole, the shock heating of surrounding material, might produce a period of enhanced emission from the galactic center. The merged system might briefly become a low-luminosity active galactic nucleus, its central black hole glowing more brightly than usual as infalling material heats to enormous temperatures. Not dangerous to Earth at this distance, but visible, a brighter than usual glow in the direction of the galactic center, persisting for millions of years. The merged galaxy is called Milkomeda by astronomers, a portmanteau that gets the job done without any pretense of poetry. It is not a name chosen to sound beautiful. It is a name chosen to be unambiguous. Milkomeda will not look like either of its parents. Both the Milky Way and Andromeda are spiral galaxies. Their stars arranged in flat, rotating disks with winding arms of brighter star formation tracing patterns around the central bulge. This spiral structure is one of the most common galactic shapes in the universe, and one of the most distinctive. When you see a spiral galaxy in a photograph, you know it immediately. The arms, the disk, the bright center, the orientation, everything about it is characteristic. Milkomeda will almost certainly be an elliptical galaxy, not a disk, not a spiral, a roughly spheroidal blob of stars, smooth, without arms, without clear rotation axis, without the flat disk structure that defines its parents. The stars of both galaxies, stirred by the gravitational chaos of the merger, will settle into orbits that are random in orientation, filling a three-dimensional space rather than a flat plane. The galaxy's rotation, the ordered spin that maintains a spiral galaxy's disk structure, will be disrupted and randomized by the merger. This is a transformation not just of appearance, but of nature. The Milky Way is a galaxy in which stars are born relatively regularly, in which the disk rotates in an organized way, in which spiral density waves drive ongoing star formation in the arms. Andromeda is similar. Milkomeda will be something different. An elliptical galaxy in which star formation has largely ceased, in which the gas that fueled new stars has been consumed or dispersed, in which the stellar population ages without significant renewal. Elliptical galaxies are, in a certain sense, galaxies in retirement. They've burned through their star-forming gas. They contain the stars they have, aging slowly, without the continuous creation of new blue-white stellar fire that gives spiral galaxies their character. The color of an elliptical galaxy is not the blue-white of young stars and active nebulae. It is the red-gold of aging stars in their long, slow decline. Milkomeda will glow red-gold. The night sky from whatever planet orbits whatever star within Milkomeda, in the period after the full merger, perhaps 6 to 8 billion years from tonight, would show this transformed galaxy not as a band of light suggesting a disk viewed from inside, not as the Milky Way's characteristic river across the sky, but as a three-dimensional haze of stars, distributed in every direction. There would be no plane of the galaxy to stand beneath. Stars in every direction, more dense toward the galactic center, in whatever direction that happens to be, fading gradually toward the edges. The sky would be different in a way that is difficult to find the right words for. Tonight's sky has a structure. The Milky Way band tells you where you are, inside a flat disk, looking through more stars in the plane of that disk, and fewer stars perpendicular to it. The structure of the Milky Way on the sky is information about your location within a shaped system. The Milkomeda sky provides no such structure. Its stellar distribution in all directions, roughly spheroidal, without the organizing geometry of a disk. You would know you were inside a galaxy. The stars would still be there, but you would not know which way the galaxy pointed. There would be no river, only a haze. The long quiet. 7 to 8 billion years from tonight. By now, the question of whether Earth still exists is genuinely pressing. The Sun, like all stars of its mass, follows a predictable life cycle. It is currently approximately 4.6 billion years into a main sequence lifetime of roughly 10 billion years. In approximately 5 to 5.5 billion years, the Sun will begin to exhaust the hydrogen fuel in its core and transition off the main sequence. It will expand. It will cool slightly at its surface, while increasing enormously in luminosity. It will become a red giant. The expansion of the Sun into red giant status is expected to eventually engulf Earth, though the exact details are debated. The Sun's mass loss during the red giant phase will weaken its gravitational grip, allowing Earth's orbit to expand outward slightly. Some calculations suggest Earth's orbit might expand just barely fast enough to stay ahead of the expanding surface. Others suggest it will not. Either way, by the time the Sun becomes a red giant, Earth's surface will have been uninhabitable for billions of years due to the increasing solar luminosity, long before the dramatic expansion phase. The Sun will then shed its outer layers in a planetary nebula, a shell of gas expanding outward from what was once a stellar surface, and its core will collapse into a white dwarf. A dense, hot, slowly cooling remnant roughly the size of Earth, containing a significant fraction of the Sun's current mass, glowing from residual heat with no ongoing nuclear reactions. Whether Earth's orbit persists around the white dwarf Sun is a question of gravitational dynamics during the mass loss phase. It's plausible. It's not certain. What is certain is that the Sun's white dwarf stage represents the final chapter of any possible history of Earth as a recognizable world. A white dwarf provides minimal heat. A planet orbiting a white dwarf exists in mere darkness, receiving a small fraction of the energy that once made its surface warm. In 7 to 8 billion years, within the merged galaxy of Milkomeda, the Sun is likely a white dwarf. Earth's fate is uncertain. Whatever life once existed on Earth's surface is long gone, or long transformed into something we cannot begin to imagine. The question of who, if anyone, is watching the night sky at this point is genuinely unanswerable. But the sky exists whether anyone watches it. And the sky at this point would be something extraordinary in a quiet way. Milkomeda, fully merged, settling into its elliptical form. The stars aging together. The hot blue giants long since exhausted, the long-lived orange and red stars still shining, the white dwarfs accumulating, the cold ashes of stars that have burned and faded. So numerous in an old elliptical galaxy that they represent a significant fraction of the total stellar mass, even though they emit almost no light. The sky of Milkomeda, 7 billion years after tonight, is the sky of deep galactic time. Not dramatic, not violent, quieter than the current Milky Way. Fewer new stars being born, The starburst of the merger long since ended. The gravitational chaos settled. Everything in orbit around everything else. Peacefully, in a galaxy that has absorbed two spiral systems and made one calm spheroid from the combination. Whatever watches that sky, if anything does, sees something that took 7 billion years to arrive at. Two galaxies, each containing hundreds of billions to a trillion stars, falling toward each other across millions of light years, interpenetrating, disrupting each other, triggering star formation and black hole mergers, and the scattering of stars into new orbits. And then, after all of that, settling, finding a shape, becoming quiet. The Andromeda collision is not a catastrophe with an ending. It is a transformation with a destination. The Triangulum problem, the third galaxy nobody talks about. Here is something that almost every explanation of the Andromeda collision leaves out entirely. Andromeda is not traveling alone. The local group, the small cluster of galaxies to which both the Milky Way and Andromeda belong, contains a few dozen members. Most of them are dwarf galaxies, small satellites orbiting the two large ones. But there is a third significant spiral galaxy in the local group, and it is already on a trajectory that will make the Andromeda-Milky Way merger even more complicated. Triangulum, officially designated Messier 33, located approximately 2.7 million light-years from Earth, just slightly farther than Andromeda, in the direction of the constellation Triangulum. It is the third largest galaxy in the local group after Andromeda and the Milky Way, containing somewhere between 40 billion and 50 billion stars. Compared to either of its larger neighbors, it's modest in size, but in absolute terms, 40 billion stars is an enormous collection. Triangulum is gravitationally associated with Andromeda. The two galaxies are close enough and massive enough relative to each other that they appear to be in a bound relationship. Triangulum orbiting Andromeda as a kind of companion, the way the Magellanic Clouds orbit the Milky Way. Some simulations suggest Triangulum has already made a close pass by Andromeda in the distant past, which would explain certain features of both galaxies' outer structures. The trajectory matters, because if Triangulum is bound to Andromeda, it is also, transitively, falling toward the Milky Way. Not as quickly, and not on as direct a path. But when Andromeda approaches the Milky Way, Triangulum comes with it. The most detailed simulations of the local group merger, not just Andromeda and the Milky Way, but all three major galaxies together, suggest that Triangulum may be involved in the merger process, either as a third participant swept up in the dynamics of the two larger galaxies, or as a body that makes a close pass by one or both of the larger galaxies before being absorbed into the merged Milkomeda system. This means the night sky transformation is not a simple two-galaxy story. There is a third galaxy to watch. Smaller, less dramatic, but present in the sky as it approaches and eventually engages with the merger dynamics. The night sky from Earth, 3 or 4 billion years from now, shows not one approaching external galaxy, but potentially two: Andromeda, the dominant presence, and Triangulum, smaller, closer to Andromeda's position in the sky. A companion galaxy being swept along by the gravitational drama of the larger collision. Most of the popular science treatment of the Andromeda collision treats this as a two-galaxy event. In reality, the merger of the local group's three major spirals is a more complex, longer-duration process that involves Triangulum as a real participant. This doesn't change the broad strokes of what the Milky Way-Andromeda collision looks like. but it complicates the long-term fate of the merged system and adds a third object to the visual drama of the sky transformation. What the simulations actually model, and why the uncertainty is larger than people realize. I want to spend some time here being honest about the precision of the timeline we've been building. Because precision and accuracy are different things, and this is a case where they diverge in a way that matters. Every number cited in this video, the 4.5 billion year collision time, the distances at each phase, the probabilities about Earth's orbital fate, comes from computer simulations of the Milky Way Andromeda system, run on astronomical supercomputers. These simulations are sophisticated. They track the gravitational interactions of millions to billions of individual mass tracers across billions of years of simulated time. They incorporate dark matter halos, stellar dynamics, gas physics, and the effects of the external environment, including the gravity of the broader local group. They are, by any measure, extraordinary scientific tools. But they depend critically on initial conditions that we measure with finite precision. And the Andromeda system specifically has a measurement challenge that has bedeviled astronomers for decades. The most critical unknown is Andromeda's transverse velocity, its speed across the sky rather than directly toward or away from us. The velocity component directly toward us is relatively easy to measure through the Doppler shift of Andromeda's spectral lines. We measure how much the light is blue shifted by Andromeda's approach and calculate the velocity. That number, approximately 110 kilometers per second, is well constrained. But the velocity component perpendicular to our line of sight, how fast Andromeda is moving sideways across the sky relative to us, is much harder to measure. It requires detecting the actual angular motion of Andromeda across the sky over time, and at 2.537 million light-years. Even an enormous sideways velocity produces an almost imperceptibly small angular motion. This requires extraordinarily precise proper motion measurements over long baselines of time. The Hubble Space Telescope made the first successful measurements of Andromeda's proper motion in 2012, measuring its sideways velocity at approximately 17 kilometers per second. This is small relative to the 110 kilometer per second approach velocity, which is why the collision is still predicted to happen. If the sideways velocity were large enough, the two galaxies might miss each other entirely, like a bullet fired just wide of its target. At 17 kilometers per second sideways versus 110 kilometers per second approaching, the trajectory bends but still intersects. But 17 kilometers per second has an uncertainty. The measurement error bars from the 2012 Hubble study allowed sideways velocities ranging from essentially zero up to about 34 kilometers per second. More recent measurements using the Gaia satellite have improved this, but there remains real uncertainty in the exact sideways trajectory of Andromeda. This uncertainty propagates directly into the simulated timeline. Different plausible values of the sideways velocity produce different simulated trajectories for the collision. The collision still happens in all plausible cases. The range of allowed sideways velocities all lead to eventual merging given the gravitational attraction between the two massive systems. But the exact timing of the first pass, the separation after the first pass, the timing of the second pass and merger, these all vary by hundreds of millions of years, depending on which initial conditions you assume. The number 4.5 billion years to the first major interaction is a median or modal result from simulation ensembles. The range of plausible answers spans perhaps 3.5 to 5.5 billion years. This doesn't change the story dramatically, but it changes the precision of the timeline we're telling. The reason I think it's worth being explicit about this uncertainty is that it's part of what makes the science interesting. We're not predicting the exact date of a train collision. We're running simulations of a gravitational system and identifying the most probable outcomes across a distribution of possible initial conditions. The collision is certain. The exact choreography is not. Every frame of the sky transformation described in this video is the modal expectation from the simulation ensemble, not a single precise prediction. The sky 3.75 billion years from tonight might look roughly as described here. Or the first pass might be 200 million years earlier or later. The qualitative story is robust. The exact timestamp is not. The local group's fate, what happens after Milkomeda forms. Zoom out, past the merger, past Milkomeda's formation, past the sun's red giant phase, past everything we've covered so far. Let's go further. Because Milkomeda itself doesn't exist in isolation. It exists in the local group. And the local group exists in a universe that is expanding, carrying distant galaxy clusters away from us at increasing speed. The local group consists of its few dozen member galaxies. Milkomeda as the new dominant member, the Magellanic Clouds, Triangulum, if it survives as a distinct entity, and numerous dwarf satellites. These galaxies are all gravitationally bound to each other. The expansion of the universe does not separate them. Their mutual gravity is stronger than the cosmic expansion within the volume of the local group. Eventually, the local group's member galaxies will all merge, not just the Milky Way and Andromeda, but all of them. Gravitational dynamics within the local group will lead, over timescales of tens to hundreds of billions of years, to a single massive elliptical galaxy containing all the stars that currently reside in all the local group's member galaxies. This final merged object, sometimes called the local group galaxy or occasionally the local elliptical, would be an enormous, old, quiet collection of hundreds of billions of stars, mostly in the orange-red end of the color spectrum, with star formation essentially ceased, sitting in an increasingly empty universe. Because here is the thing about cosmic expansion that becomes relevant on these timescales. The universe is expanding at an accelerating rate, driven by dark energy. Over billions of years, this expansion carries other galaxy clusters, the Virgo cluster, the Coma cluster, all the other groupings of galaxies beyond the local group, progressively farther away. Their recession velocity increases with time. Eventually, beyond some distance, other galaxy clusters will be receding faster than the speed of light. Not moving through space faster than light, that's forbidden by relativity. But the space between us and them is expanding fast enough that the distance grows at a superluminal rate. Light they emit after this threshold will never reach us, because the space it's crossing is expanding faster than the light can cross it. In the very far future, tens of billions of years from now, the cosmic horizon, the distance beyond which light can never reach us, will shrink around the local group. The other galaxy clusters of the universe will be pushed beyond this horizon. Their light, already faint and redshifted by distance, will redshift further until it falls below any detectable frequency, and then it will cross the horizon and be gone. The universe, as experienced from within Milkomeda or the final local group merger, will grow dark, not in a sudden event. Gradually, over billions of years, galaxy after galaxy will cross the cosmic horizon. The night sky, already lacking the Andromeda smudge that exists today, will lose other familiar objects. The Virgo cluster's galaxies will fade, redshift, and disappear. The Coma cluster will go. One by one, every object beyond the local group will be carried beyond the reachable universe. What remains eventually is a single merged galaxy, the descendant of the Milky Way and Andromeda, and all the other local group members, sitting alone in an otherwise dark universe. No other galaxies visible, no other lights beyond the stars within the merged system itself. Stars which are themselves aging, cooling, dying. The universe will be vast, dark, and populated primarily by the cold remnants of dead stars, white dwarfs, neutron stars, black holes. This is the ultimate destination of the sky transformation that begins with the Andromeda approach. Tonight's sky, with its thousands of visible stars and its faint Andromeda smudge and its view of the Virgo cluster, if you know where to look, is the richest and most populated sky this planet has ever had or will ever have. It gets less crowded from here, over billions of years. Slowly at first, then irreversibly. The Andromeda collision is not the end of something, but it is part of the long arc of something ending. The period of the universe's youth, when matter was organized into glowing structures, stars were being born, and the sky was full of light from every direction. That period is finite. We are in the middle of it, tonight. What you see from Earth at each stage, a summary. Let's put the full visual timeline in one place, as specifically as the science allows, before we close part 1. Tonight, Andromeda is a faint smudge requiring dark skies to see, visible to the naked eye as a dim oval patch about 3 degrees wide. The sky is dominated by Milky Way stars, the familiar band, the familiar constellations. 500 million years from tonight, almost no visible change. Stellar proper motion has begun to blur the constellations. Andromeda marginally brighter. Nothing dramatic yet. 1 billion years from tonight, Andromeda measurably larger and brighter, distinguishable as slightly more structured by careful observation. The Sun is 10% more luminous. Earth's surface habitability already in question. The sky transformation has barely begun. 2 billion years from tonight, Andromeda, clearly visible as a structured oval spanning 4 to 5 degrees. Its spiral structure partially resolved to the naked eye. Brighter than anything in today's sky other than the moon and planets. Beautiful and slightly threatening in scale. Dark matter halos already interpenetrating. 3 billion years from tonight, Andromeda spans 8 to 12 degrees of sky. No longer possible to miss it. Its core clearly visible, arms faintly detectable, tidal tails beginning to develop. The outer edges of both galaxies distorted. The starburst phase beginning in the overlap regions. The sky is noticeably different from anything in Earth's history. 3.75 billion years from tonight. First pass. The 2 disks interpenetrate. The sky is blanketed with stars. No dark zones between stars in the way we experience them tonight. 2 galactic rivers crossing each other across the full sky. The most dramatic sky transformation in Earth's history. 4 to 4.5 billion years from tonight. The post-first pass separation. The sky shows 2 disrupted, distorted galactic structures moving apart, trailing tidal tails, in a sky still far fuller than tonight's. Then gravity pulls them back. 5 to 6 billion years from tonight, second pass and merger. The galactic cores approach each other. The supermassive black holes spiral toward merger. The merged galaxy begins to form. The sky structure changes from two identifiable systems to one merged, chaotic, eventually settling system. The sun is a red giant or has already shed its outer layers. 6 to 8 billion years from tonight, Milkomeda, a single elliptical galaxy, red-gold light in every direction, distributed spheroidally, no disk plane. Stars aging. Star formation ceased. The sun is a white dwarf. Earth's fate unknown, but its habitability long since over. Whatever watches this sky, if anything does, sees the quiet aftermath of the most dramatic event in this galaxy's history. The number that changes everything, and why it's almost never mentioned. There is a specific number in the physics of this collision that I have been building toward, and that almost no popular explanation of this event leads with. I want to end part 1 on it, because it reframes everything else. The number is 0.0003. That's the probability, roughly 3 in 10,000, that any two stars in the colliding galaxies will have a direct physical collision during the entire merger process. 3 in 10,000 for stars in both galaxies combined, over the full duration of the merger. This number is the consequence of the enormous distances between stars even within a dense galaxy. The Milky Way contains between 100 billion and 400 billion stars, distributed across a disk roughly 100,000 light-years in diameter and roughly 1,000 light-years thick in our neighborhood. If you were to scale this down to something comprehensible, if the Milky Way were the size of North America, each individual star would be smaller than a bacterium. The vast majority of the continent would be empty space between bacterium-sized points of light. When two such structures pass through each other, the bacterium-sized stars don't hit each other. They can't. There's simply too much space between them. The probability of any two bacterium-sized objects colliding when you slide two North America-sized empty spaces through each other is effectively 0. This is the central fact about galaxy collisions that is hardest to hold simultaneously with the visual drama of what the merger looks like. The merger is visually extraordinary. Stars fill the sky in new configurations. Tidal tails stretch for hundreds of thousands of light-years. The shapes of both galaxies are permanently and dramatically altered. The galactic core burns brighter from starburst activity. The night sky transforms in ways that would seem catastrophic to any observer. And almost no stars are in danger. What changes is their orbits. What changes is the gravitational potential they're embedded in, the large-scale structure of the galaxy that defines where they move and at what speed. Stars that have been following the same orbital track around the Milky Way center for billions of years will find themselves in new orbits, some similar to the old ones, some dramatically different. But the stars themselves, the individual nuclear furnaces burning hydrogen into helium across trillions of degrees at their cores, those stars are fine. They continue burning. The planets orbiting them continue orbiting. The merger of galaxies is an event that operates at the scale of galactic structure, a scale far above the level at which individual stellar systems are disturbed. This is both the most reassuring and the most mind-altering thing about the Andromeda collision. Reassuring because whatever is alive on any planet in either galaxy during the merger has a reasonable probability of surviving the merger itself without the physical event that kills you being the collision. The death threats, if they exist, come from secondary effects: increased supernova rates from starburst activity, elevated cosmic ray flux, changes in the chemical environment of the galaxy. These are real risks, graduated and probabilistic, not the instantaneous certainty of your star being destroyed in a stellar collision. Mind-altering, because it forces you to really confront what a galaxy is. A galaxy is not a dense collection of stars, in the way a crowd is a dense collection of people. A crowd is defined by physical proximity and contact. A galaxy is defined by gravitational association. The stars in a galaxy are gravitationally bound to the same central mass, but they are individually separated by distances so vast that the galaxy's density, measured as the probability of two stars being in the same place at the same time, is incomparably lower than the density of the best vacuum humans have ever created in a laboratory. The Milky Way is mostly nothing. Andromeda is mostly nothing. When two mostly nothings collide, the result is still mostly nothing. Rearranged, what is not nothing is gravity. What is not nothing is the dark matter halos, the gas clouds, the large-scale structure. These things interact. These things are reshaped. These things drive the observable transformation of the night sky over the 4.5 billion-year timeline. But at the level of your star, your planet, your ground, the galaxies pass through each other like two ghosts walking through the same wall. The wall rearranges itself around them. Neither ghost feels the other at all. That is the Andromeda collision. Galaxy-scale transformation. Star-scale calm. The largest event in the future of our local universe, and the one least likely to directly harm anything living on any planet when it arrives. There is something almost funny about that. Almost. It is also, depending on the angle you look at it from, one of the most extraordinary things about the universe that we happen to exist in. The scale at which the drama happens and the scale at which life exists are different scales. The universe operates at both simultaneously, and we, sitting on our small planet under our temporary sky, are somehow capable of understanding both. That's where part one ends. Not with a disaster, with a clarification. The sky above you is going to change beyond recognition over the next several billion years. The galaxy you live in is going to collide with another galaxy. The night sky will, at one specific phase of that process, be so full of stars that the concept of a dark night sky will cease to exist in the way you currently experience it. And the star you orbit will almost certainly survive it, probably in a slightly different orbit, in a galaxy that no longer looks like the one it started in. But burning, still burning. The Magellanic Clouds, the preview that's already happening. Before Andromeda, there's something closer, much closer. The Large Magellanic Cloud is approximately 160,000 light-years away. The Small Magellanic Cloud is roughly 200,000 light-years. Both are gravitationally bound to the Milky Way. As satellite galaxies, irregular dwarfs, smaller and less structured than the major spirals, but containing billions of stars each. They are, right now, in the process of being absorbed into the Milky Way, slowly, over billions of years. But the process has already begun. The Magellanic Stream, a long arc of gas stretching from the Magellanic Clouds across a huge swath of the sky, is the visible evidence of this absorption already underway. The Milky Way's gravitational tidal forces have been stripping gas from the Magellanic Clouds for billions of years, pulling it out in a long trail that follows the cloud's orbital path around our galaxy. This gas bridge is a precursor in miniature of the much larger tidal tails that will develop when Andromeda approaches. What makes the Magellanic Cloud situation relevant tonight is that we can see this preview of galactic interaction with the naked eye, right now, from the southern hemisphere. The large Magellanic Cloud appears as a detached piece of the Milky Way, a bright, irregular patch of light visible in dark southern skies. The small Magellanic Cloud is nearby, smaller, dimmer, but clearly present. Two satellite galaxies in the process of being gravitationally absorbed by a larger host, caught mid-merger, observable with no equipment whatsoever from a dark field in Chile or New Zealand or South Africa. This is the Andromeda collision in slow motion, in miniature, visible tonight. The Milky Way is already doing to the Magellanic Clouds exactly what Andromeda will do to the Milky Way, pulling them apart with tidal forces, extracting their gas and stars into long streams, eventually absorbing their stars into the main galactic body. Recent simulations published in the mid-2020s suggest that the large Magellanic Cloud itself may make a close pass by the Milky Way within approximately 2 billion years, before Andromeda arrives. This pass, if it occurs, would trigger its own tidal event, tails of LMC stars pulled into new orbits around the Milky Way. The Milky Way's own disk, warped slightly by the passage of the LMC, a smaller-scale preview of the full galactic collision that follows. The Milky Way has a long history of absorbing smaller galaxies. The Sagittarius dwarf spheroidal galaxy is currently in the process of being torn apart by the Milky Way's tidal forces, its stars scattered along an arc that winds around the entire sky in a faint tidal stream. The Canis Major dwarf, the Virgo stellar stream, the Hercules Aquila cloud. All of these are remnants of dwarf galaxies that the Milky Way has absorbed over billions of years. Their identities erased, their stars dispersed into the main body of our galaxy. In roughly 10 billion years, the Milky Way will do to Andromeda what it has been doing to these smaller galaxies for its entire history. The difference is that this time, the two objects are comparable in mass. This is not a large galaxy absorbing a small one. This is two roughly equal weight fighters grappling. The outcome is not absorption so much as merger. Two large systems losing their individual identities and becoming something new. But the mechanism is the same, one already visible in the night sky tonight, in the southern hemisphere, in the Magellanic Clouds that are being slowly, patiently pulled apart by the galaxy we live in. Galactic cannibalism. It's already happening. It never stopped. What the antennae tell us: observed galaxy collisions as templates. There are approximately 2,000 observed galaxy interactions and mergers in the current astronomical catalogue. 2,000. Not hypothetical scenarios, not simulation outputs, real galaxies at different stages of their mergers, photographed from Earth across distances ranging from tens of millions to hundreds of millions of light-years. This library of observed mergers is one of the most powerful tools astronomers have for understanding what the Milky Way Andromeda event will look like. You can't watch one collision from beginning to end in real time. The timescales are hundreds of millions of years, and human astronomy is measured in centuries. But you can look at many collisions in different stages and reconstruct the sequence. The way you could understand how a fire burns, by looking at many different fires at different moments, without watching any single one from start to finish. The antennae, at 45 million light-years, are in the first pass stage. Their two dense cores are still distinct, separated by a distance of a few thousand light-years. Their disks have already interpenetrated. The tidal tails are already fully extended, each one stretching more than 100,000 light-years. The starburst regions are blazing. This is the violent early contact phase, the moment of maximum visual drama and maximum star formation activity. Farther along, NGC 7252, sometimes called atoms for peace, after the galaxy's unusual symmetry in photographs. This is a merger approximately 220 million light-years away, and it represents a later stage. The two original galactic cores have come together. The merger is substantially complete, but the resulting system has not yet fully settled into a smooth elliptical. You can still see the remnant shell structure, the tidal debris folded back into the merged system, in complex arcs. The starburst has been underway for hundreds of millions of years and has produced an enormous population of young star clusters. Farther still, the classic elliptical galaxies themselves. These are the end states. Smooth, featureless, spheroidal, the settled product of mergers whose drama has fully resolved. Many of the most massive elliptical galaxies in the universe, the giants that anchor the centers of galaxy clusters, are the products of multiple large mergers over cosmic time. They accumulated their mass through collision after collision, each one adding more stars and more dark matter to the growing system. The Milky Way Andromeda merger will pass through all these stages. The antennae snapshot shows what the first pass looks like. NGC 7252 shows what the post-merger settling looks like. The giant ellipticals show the destination. But here's what the full catalogue of observed mergers teaches us. That simple visual comparison doesn't capture. The chemistry. What the merger does to the elements, the chemistry of collision. Stars are element factories. This is one of the most important facts in all of science, and it doesn't get said often enough in plain language. Every atom in your body heavier than hydrogen was forged inside a star. The carbon, the oxygen, the nitrogen, the iron, all of it was assembled in stellar cores through nuclear fusion, scattered into space when those stars died, incorporated into the gas cloud that became our solar system, and eventually organized by chemistry and biology into whatever is reading these words. The galaxy is a recycling system. Stars are born from gas clouds, burn for millions to billions of years, and then die, sometimes quietly, shedding their outer layers in gentle planetary nebulae, sometimes violently, detonating as supernovae that scatter the products of their nuclear burning across thousands of light-years. That scattered material enriches the interstellar medium with heavier elements, which then get incorporated into the next generation of stars and planets. Each stellar generation is slightly more chemically rich than the one before. The universe started with almost nothing heavier than hydrogen and helium. 5 billion years of stellar evolution produced enough carbon to build life. The Andromeda collision accelerates this recycling. The starburst phase, triggered by the merger's gas compression, produces an enormous number of massive stars in a short time. Massive stars, those above roughly 8 times the Sun's mass, live fast and die hard. Their lifetimes are measured in millions rather than billions of years. They burn through their hydrogen fuel rapidly, fuse progressively heavier elements in their cores, and end their lives in core collapse supernovae that are among the most energetic events in the observable universe. Each supernova sprays heavy elements across hundreds of light-years of surrounding space: iron, nickel, calcium, silicon, the products of the most advanced stages of stellar nucleosynthesis. elements that can only be produced in the specific conditions of a massive star's core in the final moments before collapse. All of this gets scattered into the interstellar medium during the starburst. During the Milky Way Andromeda merger, the starburst rate will likely increase by a factor of 10 to 20 compared to the current Milky Way's star formation rate. The current Milky Way produces roughly 2 to 3 new stars per year. During the peak starburst, the merged system might be producing 20 to 60 new stars per year, heavily weighted toward the massive end of the mass distribution, because the most compressed gas clouds preferentially form the most massive stars. This burst of massive star formation and the subsequent burst of supernovae will dramatically accelerate the chemical enrichment of the merged galaxy's interstellar medium. The gas that will form the next generation of stars, the stars that will be born after the starburst phase ends, will be significantly more chemically rich than the gas-forming stars today. Planets forming around those post-merger stars will start with a more chemically complex building block inventory. More elements means more chemical complexity. More chemical complexity means a richer toolkit for the chemistry of life. The post-merger galaxy, in a very real sense, is a more life-friendly environment than either of its parent galaxies. Not because the merger made it safer, but because the burst of stellar death during the merger made it richer in the heavy elements that complex chemistry requires. This is a counterintuitive result. The merger is violent. It is destructive in the sense that galactic structure is destroyed and rebuilt. The starburst phase is hostile to existing life in some regions due to elevated radiation. But the long-term legacy of the merger is a more chemically complex galaxy, one with a richer supply of the elements that planets and life are built from. The Andromeda collision, looked at across the full timeline from its inception to its resolution, is not just a transformation of the sky. It is a chemical enrichment event. It makes the merged galaxy better at building the conditions for biology than either galaxy was before. The starburst phase in detail. What actually threatens what? Let's be specific about what the starburst phase actually means for any life that might exist during it. Because the broad statement, elevated radiation, is vague in a way that matters. The two major radiation threats from starburst activity are supernovae and gamma-ray bursts. Both are consequences of massive star death, and both scale with the rate of massive star formation. Supernovae produce several types of damaging radiation: a burst of visible and ultraviolet light, a blast of X-rays, and a long-duration increase in cosmic ray flux. The visible and UV burst fades quickly with distance and is only dangerous to surface life on a planet within a few light years. The X-ray burst is more penetrating, but also fades quickly. The cosmic ray increase, the stream of high-energy charged particles accelerated by the supernova shockwave, persists for thousands of years and can travel hundreds of light years while maintaining damaging energy levels. The critical distance for supernova-caused mass extinction on an inhabited planet is estimated at roughly 25 to 30 light years. Within this radius, the cosmic ray dose delivered over the years following a supernova is high enough to cause severe damage to complex life. Ozone layer depletion, caused by the cosmic rays driving chemical reactions in the upper atmosphere that destroy ozone molecules, exposes surface life to full solar ultraviolet radiation. This can trigger mass extinctions. At our Sun's current location in the Milky Way, supernovae are rare in the near neighborhood. The death rate of massive stars close enough to be dangerous is estimated at roughly 1 per 200 million years. Life on Earth has been exposed to multiple such events over its history. The end Ordovician mass extinction, roughly 445 million years ago, may have been partly caused by a nearby gamma-ray burst. Life survived. Severely, but it survived. During the merger starburst, the rate of supernovae within any given volume of the galaxy increases. But, and this is important, the increase is not uniform across the galaxy. Starburst activity is concentrated in specific regions, the areas where the two galactic disks have overlapped most densely, where gas clouds have compressed most severely, where the shock fronts have driven the strongest star formation. These regions are heavily concentrated toward the inner galaxy, near and between the two approaching galactic cores. Stars in the outer disk, in our region of the galaxy, would experience a smaller increase in local supernova rate. The starburst hazard is real, but geographically concentrated. An inhabited planet in the outer disk of the merged system, at something like the Sun's current orbital distance, faces a modestly elevated supernova threat during the starburst phase. Not the catastrophic bombardment of a planet in the galactic center, but a measurable increase over the baseline. Whether this increase is sufficient to sterilize Earth's surface, assuming Earth's surface still exists in a habitable state at this point, which is genuinely uncertain, is a question the models haven't resolved cleanly. The best current estimates suggest the outer disk solar neighborhood faces a supernova rate increase of perhaps a factor of 2 to 3 during the starburst peak. This roughly doubles or triples the already low background rate of dangerous events. Not zero. Not extinction guaranteed. Somewhere in the uncomfortable middle range of elevated risk. The gamma-ray burst threat is lower but more dramatic. Gamma-ray bursts are produced by a specific subset of massive star deaths, those involving rapidly rotating progenitor stars or neutron star mergers, and they release enormous amounts of energy in narrow jets. A gamma-ray burst aimed at Earth from within our galaxy would be catastrophic at distances up to several thousand light-years. Current estimates suggest Earth experiences one potentially damaging gamma-ray burst every few 100 million years on average. During the starburst phase, this rate increases. But gamma-ray bursts are also directional. The damage requires being in the jet's path, which is a small, solid angle. The increased frequency during starburst doesn't linearly translate to increased planetary risk, because most gamma-ray burst jets will be aimed in other directions. The bottom line on the starburst threat: it is real. It is elevated during the merger. It is geographically concentrated, and it represents a meaningful increase in the baseline hazard for any inhabited world in the merging system. It does not represent a guarantee of sterilization for the galaxy as a whole. Life in a merging galaxy is more challenged than life in a quiet galaxy. It is not necessarily ended. The night sky is a static object, the most beautiful sky in Earth's history. There's a question I want to sit with here, because it's not a scientific question and it doesn't have a scientific answer. And sometimes, those are the questions worth sitting with longest. Is the sky during the first pass the most beautiful sky that Earth has ever had, or will ever have? Think about what it would look like. We built this picture in part 1, but let's slow down on it tonight. The first pass happens approximately 3.75 billion years from now. The two galactic disks sweep through each other. Andromeda's trillion stars are no longer a smudge of light in one direction. They are distributed across the sky. Their orbital positions around Andromeda's center mapped onto the celestial sphere from Earth's perspective, creating a second river of light that crosses the Milky Way's own river. Two galactic bands, two rivers of stars, crossing each other at an angle determined by the exact geometry of the approach. probably somewhere between 30 and 60 degrees, creating an X across the sky, or a crossing pattern, like two contrails from different aircraft fading across the same sky at different angles. The individual stars visible to the naked eye, which are determined by brightness and distance, would be enormously more numerous than tonight. Currently, from a perfect dark site, roughly 9,000 stars are visible to the human eye. During the first pass, the answer is more complicated. Andromeda's stars are still mostly too distant and too dim to appear as individual points. The bulk of the increased sky brightness would come from the aggregate glow of Andromeda's unresolved stellar population, not from individual new stars. But there are exceptions. The brightest stars in Andromeda, supergiant stars, the luminous monsters that outshine our sun by tens of thousands to millions of times, would be individually visible even across the distance of the merged system. Blue hypergiants, red supergiants, luminous blue variables. These are stars so intrinsically brilliant that at any distance achievable during the merger overlap, they would appear as bright individual points, adding to the sky's stellar population. The starburst regions would be spectacular. Tight clusters of newly formed massive stars blazing in the blue-white light of hot plasma, scattered across the sky in the regions where the gas clouds have compressed and ignited. These clusters, called superstar clusters, contain tens of thousands to millions of young stars packed into regions just a few tens of light years across. From Earth's distance, they would appear as bright knots in the sky, individual objects far brighter than any individual star, glowing blue-white with the combined light of their thousands of members. The tidal tails, long arcs of stars drawn out from both galaxies by the gravitational encounter, would be visible as faint structural features, arching curves of diffuse light extending across significant fractions of the sky. Not as bright as the main galactic bands, but visible, adding to the complex texture of the sky. And then there are the nebulae, the compressed gas clouds that haven't yet collapsed into stars, the ones that will, in another million years, form the next generation of suns, glow in the light of the massive stars already burning nearby. Emission nebulae, huge clouds of ionized hydrogen lit from within by the ultraviolet radiation of hot young stars. Glow in pinks and reds that human eyes can barely detect, but that would be unmistakable against the dark background of a clear night. During the starburst, these nebulae are more numerous, brighter, distributed across the sky in the merger regions. The total luminosity of the sky during the first pass, the total amount of light falling on a dark surface on Earth, coming from all directions from the stellar background, would be measurably higher than tonight. Not dramatically, not enough to interfere with sleep, but enough that the darkest parts of the night sky would be perceptibly brighter. The sky between the galactic bands would glow faintly from the collective light of a trillion unresolved stars. A diffuse luminosity that fills in the darkest regions, the way a thin layer of clouds diffuses moonlight. Has Earth ever had a sky like this before? The answer is no. In Earth's early history, when the planet formed roughly 4.5 billion years ago, the Sun was less luminous, and the galaxy was more active, more star formation happening. The Milky Way younger and richer in massive stars. But the Andromeda collision had not yet begun, and the sky from early Earth, while containing the Milky Way band roughly as we see it today, did not contain Andromeda's trillion stars distributed across its structure. At no point in Earth's 4.5 billion year history has the sky looked like what it will look like during the first pass. The night sky above dinosaurs, above the first fish, above the cooling surface of the newly formed planet. None of these skies had a second galactic band crossing the Milky Way. None of them had the starburst knots, the visible tidal tails, the combined light of 2 trillion stars distributed across the full celestial sphere. The first pass sky is unique in Earth's history. Not just unusual, unique. It has never existed before, and once the merger is complete and the 2 galaxies have settled into Milkomeda's smooth elliptical structure, the dramatically full and structured sky of the first pass will be replaced by the quieter, spherically symmetric haze of the merged system. The crossing galactic bands will dissolve. The tidal tails will be reabsorbed. The starburst will wind down. The most dramatically beautiful night sky this planet will ever experience exists approximately 3.75 billion years from tonight. For the organisms, or whatever other forms of awareness exist at that moment, the sky above them is unlike any sky any consciousness in Earth's history has ever experienced. They will not know that. They will not know that 3.75 billion years ago, there were creatures on this same planet staring up at a relatively empty-looking sky, a Milky Way band, a faint Andromeda smudge, the same stars in their familiar positions. And those creatures wondered what the night sky would look like when the galaxies finally met. And the answer was, like that. Like the sky they're standing under right now, looking up, perhaps finding it perfectly normal. That's how it usually goes. The extraordinary becomes the background. The unprecedented becomes the baseline. Whatever consciousness exists under that sky 3.75 billion years from tonight will probably find it unremarkable. Will probably not know they are standing under the most visually complex and structurally rich night sky this planet has ever held. What carries memory? The question underneath the physics. I want to spend the final section of part 2 on the question that the science cannot answer, because it's the question that the whole timeline eventually leads to, and pretending the physics settles it would be dishonest. Across the 4.5 billion years of the Andromeda collision's timeline, Earth becomes uninhabitable. Not because of the collision, because of the sun. The sun's brightening, its eventual red giant phase, the ultimate collapse to a white dwarf. These are all certainties that play out across the same general time frame as the merger. Earth's story and the galaxy's story run simultaneously, and Earth's story ends first. But something might not end with it. Life has been on Earth for roughly 4 billion years. In 4 billion years, it has gone from self-replicating chemistry in warm, shallow seas to organisms that build telescopes and detect colliding galaxies and write scripts for strangers to listen to at night. The trajectory of that 4 billion years, from chemistry to consciousness, from single cells to civilizations, is not obviously complete. There is no reason to think that whatever exists 4 billion years from now, in whatever form it takes, has reached the end of that trajectory. If anything survives Earth's eventual uninhabitability, if life moves, or is moved, or transforms into something that can persist elsewhere, then the collision of galaxies becomes not a backdrop to human extinction, but a backdrop to human continuation in some form. The starburst phase produces new stars and new planets. The merged galaxy's chemical enrichment produces planets with richer element inventories. The gravitational reshuffling of the merged system produces new orbital arrangements, new habitable zones, new sites where the chemistry of life might take hold. Whether anything that began on Earth still exists in any recognizable form 4 or 5 billion years from now is genuinely unanswerable. The question involves technological development trajectories, the long-term survival of intelligence under the increasing solar luminosity, the possibility of migration off Earth before it becomes uninhabitable, and thousands of contingencies that we have no way to predict across such timescales. What we can say is this: the universe does not stop providing opportunities. The merger does not close off the conditions for life. It reshapes them. New stars are born during the starburst. New planets form around those stars. The chemical palette available to those planets is richer than what was available when Earth formed 4.5 billion years ago. Whatever comes after us, whatever forms of matter organized into awareness exist in the merged galaxy 5 or 8 billion years from tonight, they will have opportunities the universe has never before provided. The collision is not the end of the story. It is a chapter break. Whether anything that was once us is there to read the next chapter, that we don't know. That we can't know. But the chapter exists. The universe continues. The sky above whatever lives there is extraordinary in ways we can now, sitting here, imagine. The question nobody asks about the collision. Most discussions of the Andromeda collision focus on the collision itself, what it looks like, what it does, when it happens. Nobody asks the quieter question that follows from all of it. Why are we here for this particular moment? We exist at a very specific point in the timeline. The universe is 13.8 billion years old. The Milky Way formed roughly 13.5 billion years ago. Earth formed 4.5 billion years ago. Complex life appeared roughly 540 million years ago. Humans roughly 300,000 years ago. Modern civilization roughly 10,000 years ago. Modern astronomy roughly 400 years ago. We have been capable of understanding the cosmos for an eye blink of its history. And in that eye blink, we happen to exist at a moment when we can see Andromeda clearly, measure its distance precisely, calculate its trajectory confidently, and predict the merger with reasonable accuracy. We happen to exist when the collision is still far enough away to be understood as a future event rather than an ongoing one. We happen to exist in the brief window when both galaxies are distinct, separate, clearly visible as different objects in different directions of the sky. If we had evolved 5 billion years earlier, Andromeda would be twice as far and harder to see. If we had evolved 5 billion years later, inside Milkomeda, if anything of us survived that long, there would be no Andromeda to observe. The two-galaxy sky would already be a one-galaxy sky. Future intelligences inside Milkomeda with no external galactic records might have no evidence that their merged galaxy was ever two separate spirals. They might reconstruct it from the structure of stellar populations within Milkomeda. The chemical and kinematic signatures of the two original populations still detectable within the merged system. But they would not look up and see it. We look up and see it. Two galaxies, still separate, the smudge of Andromeda in one part of the sky, the Milky Way band across the other. The relationship between them not yet visible to the naked eye in terms of scale. Andromeda still looks small, manageable, a distant object rather than an incoming one. But the physics is already locked in. The trajectory is set. The collision is happening. Just slowly. We exist at the last moment, when the galaxy we live in is still cleanly itself. Before the merger begins in earnest, before the sky starts to transform, before the tidal tails develop, and the starburst ignites, and the night fills with the light of Andromeda's trillion stars. We are the last generation, not of humans, but of anything. to see the Milky Way as a distinct, uncompromised galaxy in a sky where Andromeda is merely a faint suggestion of what's coming. That is either a remarkable privilege or simply where we happen to find ourselves in the timeline. Maybe both. The answer depends on how you look at it. And how you look at it depends on whether you think the universe is the kind of place that has moments worth paying attention to, or whether all moments are equally arbitrary and any attempt to find significance in your particular position in time is just a story you're telling yourself. I think it's worth paying attention. I think the sky above your head tonight, this specific configuration of stars and galaxies, and the faint smear of Andromeda in its current direction, at its current distance, is worth a moment's actual notice. Not just as physics to understand, but as a sight to experience. You are standing on a planet that has been here for 4.5 billion years, and has roughly 5 billion more to go before the sun makes it unlivable. You are looking at a sky that has never looked quite like this before and will never look quite like this again. Every single star in that sky is moving. Andromeda is moving. The universe is expanding. The pattern is temporary, and you are standing in the specific sliver of time when it looks exactly like this. You just happen to be here for it. What carries memory? The question underneath the physics. I want to spend a section on the question that the science cannot answer, because it's the question that the whole timeline eventually leads to. And pretending the physics settles, it would be dishonest. Across the 4.5 billion years of the Andromeda collision's timeline, Earth becomes uninhabitable. Not because of the collision, because of the sun. The sun's brightening, its eventual red giant phase, the ultimate collapse to a white dwarf. These are all certainties that play out across the same general time frame as the merger. Earth's story and the galaxy story run simultaneously, and Earth's story ends first. But something might not end with it. Life has been on Earth for roughly 4 billion years. In 4 billion years, it has gone from self-replicating chemistry in warm, shallow seas to organisms that build telescopes and detect colliding galaxies and write scripts for strangers to listen to at night. The trajectory of that 4 billion years, from chemistry to consciousness, from single cells to civilizations, is not obviously complete. There is no reason to think that whatever exists 4 billion years from now, in whatever form it takes, has reached the end of that trajectory. If anything survives Earth's eventual uninhabitability, if life moves, or is moved, or transforms into something that can persist elsewhere, then the collision of galaxies becomes not a backdrop to human extinction, but a backdrop to human continuation in some form. The starburst phase produces new stars and new planets. The merged galaxy's chemical enrichment produces planets with richer element inventories. The gravitational reshuffling of the merged system produces new orbital arrangements, new habitable zones, new sites where the chemistry of life might take hold. Whether anything that began on Earth still exists in any recognizable form, 4 or 5 billion years from now, is genuinely unanswerable. The question involves technological development trajectories, the long-term survival of intelligence under the increasing solar luminosity, the possibility of migration off Earth before it becomes uninhabitable, and thousands of contingencies that we have no way to predict across such timescales. What we can say is this: the universe does not stop providing opportunities. The merger does not close off the conditions for life. It reshapes them. New stars are born during the starburst. New planets form around those stars. The chemical palette available to those planets is richer than what was available when Earth formed 4.5 billion years ago. Whatever comes after us, whatever forms of matter organized into awareness exist in the merged galaxy 5 or 8 billion years from tonight, they will have opportunities the universe has never before provided. The collision is not the end of the story. It is a chapter break. Whether anything that was once us is there to read the next chapter, that we don't know, that we can't know. But the chapter exists. The universe continues. The sky above whatever lives there is extraordinary in ways we can now, sitting here, imagine. There is something in the structure of that sentence worth staying with for a moment. We can imagine it. We, now, in our brief flicker of existence, in this specific century, on this specific planet, can run the physics forward and construct a picture of the sky 4 billion years from tonight. That is probably approximately correct. We can see, in our minds, the two galactic bands crossing each other during the first pass. We can feel, in some approximate way, what it would mean to stand under that sky. No other moment in Earth's history has produced anything capable of that. The dinosaurs under their Cretaceous sky could not imagine the sky 4 billion years from their moment. The first fish could not. The first cells certainly could not. Only now, in this eye blink of cosmological time, does the universe contain anything that can look at the sky and think forward 4 billion years and see, however approximately, what comes next. That capacity, the capacity to model the future of the sky itself, is one of the strangest and most recent developments in the universe's history. And it is ours, right now, in this moment. The merger will happen whether we model it or not. The sky will transform whether we understand it or not. But understanding it means something, not to the universe, which has no preference, but to us, and to whatever comes after us, if it inherits the records we leave. The knowledge that the sky is going to change like this, the specific, numbered, time-stamped knowledge of what happens and when and why, is the kind of thing that, once known, doesn't need to be rediscovered. It can be inherited. It can be passed forward in whatever form information takes, across whatever successors we produce. Future minds, in whatever substrate they run in, can start from knowing the sky's future rather than having to rediscover it. That's not nothing. That's actually a lot. The very last thing before sleep. But before we get there, one more section, because there's a dimension of this event that I've been working around all night, and that deserves to be named plainly. The Andromeda collision is going to happen whether we understand it or not, whether we're here or not, whether any life is here or not. The gravitational mechanics are set. The trajectory is locked. The only variable in the entire 4.5 billion year story that involves us in any meaningful way is whether something aware of the event is present at any given stage of it. To say, this is happening, and it is remarkable. That variable, the presence of awareness, of something that can register the event as significant rather than just experience it as physics, is not guaranteed at any stage. We are present now. We are aware of it now. We understand the timeline, the stages, the numbers, the visual transformations, the chemical consequences, the gravitational dynamics. We carry this knowledge right now, in this specific year, on this specific planet, as the specific form of organized matter that happens to have evolved consciousness capable of modeling the future of its own galaxy. That is genuinely unusual, maybe uniquely unusual, though we don't know. The universe may contain other forms of consciousness elsewhere, in other galaxies, at other stages of their own cosmological timelines. Those other consciousnesses, if they exist, may also be modeling the future of their local sky, working out the trajectories of their nearest galactic neighbors, understanding that their current sky is temporary and the next one is already in motion. But we don't know they're there. We only know we're here. And we're here for this. What does it mean to be aware of the merger? What does it add to the merger itself? Physically, nothing. The gravitational waves propagate identically whether anyone detects them or not. The tidal tails form with equal mathematical precision whether anyone traces their arc or not. The starburst ignites and the supernovae scatter their heavy elements whether anyone catalogues the chemical yields or not. The physics doesn't consult awareness before proceeding. But meaning is not a property of events. It is a property of the relationship between events and the minds that experience them. The merger has no meaning on its own. It acquires meaning in the relationship between itself and the consciousness present to receive it. We are the meaning makers. That is not a small job. In a universe this large, running on physics this impersonal, the emergence of anything capable of finding the process significant, of standing under a sky and feeling something about it, of tracing the trajectory of a galaxy and calling it beautiful, or terrifying, or both, is the most remarkable development in the universe's 13.8 billion year history. Or if not the most remarkable, then among the most remarkable. The emergence of stars from gas clouds was remarkable. The formation of planets from stellar debris was remarkable. The self-replication of complex molecules was remarkable. The evolution of nervous systems was remarkable. The emergence of consciousness was remarkable. And consciousness that models the future of its own galaxy, consciousness that can sit with a cup of tea at midnight and understand, roughly but genuinely, what the sky above it will look like 3.75 billion years from now. That is the latest remarkable development in a long chain of them. You are part of that chain, not a passive part, the active part, the part that receives the physics and converts it into meaning. The part that takes the merger, a gravitational event involving 2 trillion stars crossing paths over 4.5 billion years, and makes it a story worth telling, worth hearing, worth lying in the dark thinking about. The merger will happen. The sky will change. Milkomeda will form. The universe will continue. In all of that vast, impersonal, beautiful machinery, the one component that was never guaranteed, and that matters in the only way that meaning can matter, is the part that notices. Tonight, you're the part that notices. That's not nothing. That's actually everything that the universe can produce that is worth calling significant. The one that, if you're lying in the dark and the sky is above you through the ceiling, will give you something exact to hold. Right now, Andromeda is approaching at roughly 110 kilometers per second in its line of sight component. That is 396,000 kilometers per hour. In the time it takes you to fall asleep tonight, let's say 20 minutes, Andromeda will have moved roughly 132,000 kilometers closer to the Milky Way. 132,000 kilometers. The distance from Earth to the Moon is roughly 384,000 kilometers. In the time it takes you to fall asleep, Andromeda moves about a third of the Earth-Moon distance closer. And it has been doing this for longer than Earth has existed. Every night for 4.5 billion years, while nothing on Earth was watching, Andromeda moved its incremental 132,000 kilometers per 20 minutes closer. The total distance covered is staggering. What remains is still 2.537 million light-years, but less than it was. Always less than it was. The collision is a product of trillions of those 20-minute intervals. Each one almost nothing. All of them together. Everything. That's the structure of cosmological time, applied to the experience of a single sleepless night. The universe is patient in a way nothing biological can match. It accumulates. It compounds. It carries forward without remainder or distraction. And over enough of these 20-minute intervals, galaxies collide. You don't have to stay awake for it. The universe doesn't need you present. The motion continues while you sleep, while you dream, while you wake and go through your day and sleep again. The same way it continued before you were born. The same way it will continue after. The only difference, the only actual difference, is that you can know about it, that you can hold, for the duration of whatever attention you can muster, the idea that you are on a planet inside a galaxy that is falling toward another galaxy, and that the sky above your head is already wrong in the river photograph sense. Already a snapshot of something that is moving. Already a frame of a longer film that will play out across timescales no human will ever fully witness. That knowledge doesn't change what happens, but it changes what it means to be here for it. There's one more number worth carrying into sleep. The combined mass of the Milky Way and Andromeda, dark matter included, is estimated at roughly 4 to 5 trillion solar masses. 4 to 5 trillion times the mass of the Sun, bound together by gravity, falling toward a shared center of mass that neither galaxy is actually at, drifting slowly toward the place where the combined center of mass will eventually sit. 4 to 5 trillion solar masses, moving toward each other for the last 4 billion years, and for the next 4 billion. The thing is that none of that mass knows it is part of the story. None of it finds the merger significant, or terrifying, or beautiful. The dark matter doesn't care. The stars don't care. The gas clouds don't care. The black holes, when they finally spiral together and merge and send gravitational waves across the observable universe, won't care about that either. Only you do. Only the specific configuration of matter that evolved on one small planet around one ordinary star, somewhere in the outer disk of one of those two approaching galaxies. Only that specific arrangement has any experience of the event at all. You are the universe's witness to its own collision, the rarest possible participant in the most inevitable possible event. Tell us in the comments where you are right now. Not metaphorically. Literally. What city? What country? What hemisphere? Because we have been talking for 2 parts now about the sky above Earth changing beyond recognition, about constellations dissolving, and Andromeda growing, and 2 galactic rivers crossing the night. And the sky above Earth is not one sky. It is the sky above United States right now, and the sky above Australia right now, and the sky above Singapore and Canada and Japan and New Zealand and everywhere else, simultaneously. The same physics, the same approaching galaxy, the same 132,000 kilometers per 20 minutes, but different stars visible overhead, different seasons, different depths of night. The community that listens to this channel is, somehow, distributed across that sky. People in different hemispheres, under different sections of the Milky Way band, looking up at different stars from the same catalogue, all in the same night, thinking about the same approaching galaxy. There is something about that specific geography. One topic, one night, different pieces of the same sky, that feels important to acknowledge. So tell us where you are. Under which part of tonight's temporary sky? In which specific corner of the planet that will, in 3.75 billion years, have a completely different sky above it? And if this kept your brain company through the night, if part 1 and part 2 together gave you enough to think about that the other thoughts had less room, like the video, subscribe to Calm Theory for sleep and come back for the next one. We will always have another question. The universe is not running out of them. Good night. For real this time.